We have magic. I'm going to teach you how to do math magic, at least the starting spot of math magic today. It's an amazing concept. It's called constrained optimization, and we're going to learn about something called LaGrange multipliers. We've done unconstrained optimization. It's called absolute max and min. We did in the last section, right, 13.8. We've also done constrained with 3 variables, but if you notice, we had to change one of those variables into the other 2 to do it. I'm going to show you how to eliminate that necessity. Here's the idea. All we're going to do today is talk about the idea. We're going to get down to at least the equation, what I want you to know, introduce the Lagrange multiplier, and that's it. So here's the idea. Take a function. Notice a 2-variable function. This is a surface. And take a constraint. Where C is a constant. Listen carefully because I do not want you to miss this. Recognize 2 independent variables equal to a dependent variable. This is a surface, correct? Recognize 2 independent variables equal to a constant. This is a level curve to a surface. Do you see it? This is a level curve to some function. That should make some sense. If that's a surface, and I let the surface equal a constant, I get a level curve to the surface. Should Vince feel okay with that one? Now, consider this. If I set, please watch carefully. You don't blink. You'll miss it. You'll miss it if you blink. If I start setting this one equal to constants, I'm going to get a whole bunch of level curves. You guys get it? A whole bunch of them. So let's look at some just made up old level curves. Level curves of f of x equals c1, c2, c3. It doesn't matter. We're getting some level curves on that surface. And let's look at this level curve. Check it out. I lost it. If this is a surface, it's going to have a whole bunch of level curves at different values of c. Do you follow me? This is already a level curve. The point is there is going to be an overlay of the level curves of this surface that equal to different values c. You're getting different level curves. There's going to be a contour plot. You see all the different level curves. We've talked about it before. There's a whole bunch of them. But that's also a level curve. Verify something. This and all of these are on the same plane. That means there's going to be some overlay. Let's call this the level curve. This one. There's going to be an overlay. These level curves are going to intersect. Do you get it? Here's the beautiful thing about it. If we're on a function, but we're also given a constraint, listen carefully. We have to be on the surface. You with me? We have to be on one of these level curves. We also have to be on this specific level curve, where these level curves intersect this level curve. Do you guys see that we have to be on both? We've got to be on both. We have a constraint. We have to be on this. We have a function. We have to be on this. We're on all these level curves, but we're bound to this one. This is our constraint. It constrains our outcomes. This level curve is going to intersect these level curves. Where they do, if that's a contour plot, notice that these level curves are giving different heights. Different heights. don't know why I said that so intensely. Different heights! We're getting different heights. This is either falling, look carefully. These level curves are either falling away or they're climbing upwards. That means wherever this guy intersects them, we have different values of our function. Where it bounces off one of them, we will either get a maximum or a minimum. Because either it's dropping away or it's climbing up. Do you see it? This is what we're looking for. Everything else is going to be higher and or lower. And either one. It's going to be higher or lower than that point. So this right here, that right there, gives us where these things intersect, give us constrained maxima or constrained minima. I'm ready for it. Are you ready for it? This could blow your minds. It's going to absolutely blow. It's going to crush your heads. Ready? You're going to love it because it's going to put all of chapter 13 completely together for you. Promise. But you got to stick with me. Number one. Do you guys get the surface level curves? This is a level curve of some surface, and the level curves are going to intersect if we're going to have any solutions. You guys get it? Do you understand the concept that if we bounce off, if these level curves are falling or climbing, that guy right there is going to be an absolute max or an absolute min for that constraint. Do you get it? Don't know which one, but these are giving us different intersections, different outcomes. Check it out. We're looking for the one that we bounce off of. Now, how about this? If we bounce off, if the level curves bounce off each other, if two curves intersect at one and only one point, they share a common tangent. Or at least, their tangents are scalar multiples. I'm not writing all this down. You're going to have to listen to it a couple times if you don't catch it. I don't have time. Their tangents are scalar multiples. Do you get it? But there's more. Oh my gosh, there's more. There's more. If they have the same tangent, tell me something about their normals. Same normals. Do you get that if they bounce off each other, they have a common tangent? If they bounce off each other, they also have a common normal. They have a common normal vector. Or at least the normals are scalar multiples. I'm sorry, the normals of the level curves are scalar multiples. Here's the magic. Here's the magic. Keep on saying that. Here it is. So the normal for this surface is equal to k times, let's call it a constant for right now. I'm going to change it constant in just a second. K times the normal to this function. Bear with me. Level curves of f. The level curve, listen, don't just wait for a second before you write that down. I need your eyes right here. The level curves of f, correct? The one level curve we care about for g. This level curve is a level curve of some higher function. So the normals for this function are scalar multiple, just k times, just constant, times the normal to this function. That's saying that their level curves have the same normal, or scalar multiple the same normal. And not? Put all of your knowledge of all this chapter together. What gives you normals to level curves? Normals of the level curves. Gradient. That means the gradient for f must be a scalar multiple of the gradient of g. Has to be. Here's what we call that constant. That scalar multiple has a special name. That scalar multiple is called lambda, and that right there is what we define as the Lagrange multiplier. Multiplier, scalar multiple, the Lagrange multiplier. That's what it is. The most important part is that this can be extrapolated for 3 dimensions, which means that when you get optimization with 3 dimensions, you don't have to change a variable anymore. Because gradients work like that, gradients give you normals of level curves or level surfaces. And since those normals have to be identical, or at least scalar multiples, we get the gradient for f has to be a scalar multiple, we call it the Lagrange multiplier, for the gradient of g, no matter how many variables I have. That is fantastic. Level curves have to intersect. We're looking for the one that bounces off. If it bounces off, has the same tangent, scalar multiple. Same normal, scalar multiple. So if we go back to the surfaces that created our level curves, the gradient gives us the normals to those surfaces. The gradient gives us the normals to the level curves. Gradient gives us normal to the level curves. They have to be scalar multiples. We just showed why. Same tangent, same normal. Therefore, we call that scalar multiple, Lagrange multiplier. Now that's how we're going to start doing constraint optimization. I'll show you exactly how it's done next time, but do you see where it comes from? Show of hands if that makes sense. Sweet. Okay, so welcome back to Lagrange multipliers and constrained optimization. I'm going to do a little recap because I know it's been a few days for us. So we're going to come back at it. It's going to be a brief recap, but here's what we're learning about section 13.9. This is just the continuation of that. Here's our idea. Our idea is, suppose I give you some function, verify it's a surface. Are you guys alive? Yes. Oh, okay. And suppose I give you a constraint. Well, if I give you a constraint equal to a constant, how our constraints are, this is a level curve to some other function, some other surface. So let's check it out. Surface? Yes. Surface? Yes. Is this going to have level curves? In fact, if I set this equal to a constant, I create a lot of constants. I create a lot of level curves. So take our function, our surface, set it equal to a constant. It's going to create a whole bunch of level curves. Make sense? Now this constraint, it's already set equal to a constant. This is a specific level curve. So here's what I'm looking for with our constrained optimization. In constrained optimization, you do have to be on this surface, which means you're going to be on these level curves. Does that make sense? But you also have to be on this constraint. So you have to be on this specific level curve. If I were to draw both of them, look, this surface has a whole bunch of level curves, okay? This surface has a whole bunch of level curves. This is one specific level curve, the constraint that we have to be on. Do you guys see the difference? There's a whole bunch of level curves for this, but there's only one that I care about for that surface, the one equal to the constant that gives us that constraint. So, okay, fantastic. These level curves are going to intersect. If there's going to be any solutions, they're going to intersect. So, the level curve, this constraint, is going to intersect a whole bunch of these level curves for that surface. Do you guys get the idea? What we're looking at is for the point where this constraint level curve bounces off one or more of the level curves of the other function. Why we care about them bouncing off, why we care about them intersecting at one point is this. If I'm going to map the level curves of this surface onto a plane, which is exactly what I've done, that's a contour plot. And what that means is that from here, look carefully please, from here to here, and here, the function is either falling or the function is climbing. Does that make sense? So if I look at here or here or here, this function right here is either higher or lower than this. here, it's either higher or lower than this. So that one point, if I think about the contour map, this is either going to be a high spot or a low spot. Consider the contour map. These things are either falling away or they're climbing, correct? So where they intersect, these points are all higher or lower than that. What that means is that this point where we bounce off, where one level curve, the one we care about, the constraint, intersects a level curve of the other function, the function where we're trying to maximize or minimize, where they bounce off, we either get a high point, constrained maximum, or a low point, a constrained minimum. Did you guys get the idea of the contour plot? That the contour plot is shaping the surface, it's showing the shape of the surface. It's either falling away or it's climbing up. Do I know which one? Not really. I don't really care. Because what I care about is that it's going to be one of them. We have other things that we can do to figure out whether it's max or min. The point is, at that one spot, where we touch at one spot, that creates a high point of a surface like this, or a low point of a surface like that. Does that make sense? That's the whole point. Now we start studying it. Surface? Yeah. But we set it equal to constants, and we get a lot of level curves. Surface? Yeah. But we set it equal to a specific constant to get a constraint. That's one specific level curve where they bounce off. That's what we're looking for, constrained max or constrained min. Now we studied the idea of that. If a function intersects another function at one point, they're said to have a common tangent, or at least their tangents are parallel. So let's put this into perspective here. Please listen carefully. The level curves, level curve, have parallel tangents. Do you follow that? Okay. You say common tangent or parallel tangents. However, if the level curves have parallel tangents, think about this. If you have parallel tangents that are like this, parallel tangents, are your normals also parallel?
Yes.
Yeah, I feel like I'm in a box of emotion. So if your tangents are parallel, the level curves also have normals that are parallel. Level curves have parallel tangents? Check. Level curves have parallel normals? Check. That's what we're talking about. The normals to these curves at that point is common, or at least they're parallel. And now that you're with me. Now, normals are vectors. Tell me something you know about vectors if they are parallel. Tell me something about that. Scalar multiples. So if our normals, listen, as we're putting together, okay, so the equation I gave you last time actually makes sense to you now. If the normals are parallel, the normals of these level curves must be scalar multiples. Do you guys get that idea? So the normals must be scalar multiples. Level curves of F? Yep. Level curve of G? Yep. What I know is that the normals to those level curves at that one point, the normals to those level curves have to be scalar multiples. So the normals to level curves of f of x, y, is k times, let's call that a constant. Just some scalar, a scalar multiple to the normals of the level curves of g of x, y. Do you guys see that what we just spoke about is written down in this kind of verbal model here? If we said this, the level curves have parallel normals. The level curves have parallel normals. Oh, they're scalar multiples of each other. Show of hands, feel okay with the idea, for real. This is the idea of constraint optimization. This is the idea of something called a LaGrange multiplier. What we do is we think back a little bit. Hey, everybody, what gives us normals to level curves? What gives us normals to level curves of a surface? What gives us that we've been doing for the gradient? Did you follow this? Here's a function, right? It's a surface. If I find the gradient gives me normals to the level curves. You get me? Here's a function. It's a surface, but that's a level curve. The gradient would give me the normal to this specific level curve, the one I really care about. I know that those normals have to be scalar multiples. The gradient gives me normals to level curves. The gradient gives me normals to level curves. So we go, okay, so the gradient of f must be a scalar multiple of the gradient of g. Did you catch on to that? Saying the same thing twice. Here's the deal. We just don't call it k. We call it lambda. It's called the LaGrange multiplier, and it's a scalar. This is all I'm trying to say. It's how constrained optimization works. Here's what it says. Here's what it says. One last time, okay? Check it out. So you should bear with me because the examples are coming. We only have 3 of them. We're going to get them done in about 25 minutes. But that's it. So here we go. This gives us normals to level curves, correct? The normals to these things I'm looking at. This gives us normals to level curves. The normal to this one that I'm looking at. Makes sense? If they touch at one point, they will. If they touch at one point, their normals have to be scalar multiples. So by making our normals scalar multiples, we find the point. So we're going to find the one point or more points where we have normals that are scalar multiples. You guys get it? At that point, our normals can be scalar multiples. So make our normals scalar multiples, and we can find the point. We're kind of working backwards here. Does that make sense? Kind of cool, right? You know the gradient means normals to level curves. So we use that. We say we want to find the point where the normals are scalar multiples, where they are parallel, where they have basically the same normal. That's where our one level curve constraint intersects another level curve of our surface, the function. Let's try an example with this. I'll show you how it's done. I got to tell you right now, we're not going to be focusing on word problems because they take a long time. I'm focused on setup and the operations behind them. Word problems do happen. I'm not going to be super concerned about it. I think that you guys can manage it. What I do care about is you going about doing these problems. And not if you're okay with the idea before we go any further. Okay, so how we do it. Well, the first thing I want you to do is recognize that I'm giving you a surface here and a constraint here. Here's what I want you to do first. The whole goal, where my pants go, the whole goal is to find lambda. That's a horrible lambda. To find lambda. So, now here's what's kind of nice. We already have a function f. Do you remember? You remember a while back when I gave you like 2x plus 3y equals 6, and I said, hey, I want you to pretend that's a level curve. So you're going to find the function higher. That way the gradient gives me the normal to that. Do you remember doing that? It was when we found tangent planes, normal lines, all that sort of stuff. That's what we're going to do. So let's do that here real quick. I already have a function f, but I'm going to create a function g such that that is a level curve. It's not hard. It's not hard. All you got to do is put the function without the constant. So what's g of xy going to be, everybody, please?
2x plus 3y.
Yep. Okay, let's just bear with me here for a second. Is this one specific level curve of this function?
Yes.
Yeah, namely the one I said equals 6. That's a level curve. That's what we're doing. Now, come on, put it together. What gives us normals to level curves? So now that I have a function, 2 variables, and a function, 2 variables, all we gotta do is find the gradient, because the gradient is gonna give us the normals to that function's level curves. And the gradient is gonna give us the normals to that function's level curves, including that one, the one I care about. So let's go ahead and do this right now. Can you find gradient of f and gradient of g? Do you remember how to do the gradient? It's been a while. You take the partial derivative with respect to xi plus the partial derivative with respect to yj. That's all you got to do. So for f, the del, gradient of f is y. Good. yi plus xj. Head nod if you're okay with that one. How about for the g? Do I take the gradient of this one? That's already a level curve. I want to take the gradient of the higher function. That way it gives me the normals to the level curve that I'm looking for. So the gradient of this gives us, come on, quickly.
2y squared plus 3j.
Should fans feel okay with that? It's not hard. We spend a whole lot of time so you get the understanding. Here's what we've done so far. Please look carefully. Here's what we've done. We've found an equation that will give us the normals to all of the level curves of that surface. Basically, we found the equation that's going to give us the normals to all of these little black circles here. That makes sense? We've also found the equation that's going to give us the normal to anything on this level curve itself. What we're looking for is the place where they're equal, or at least scalar multiples. That's what this says. Find the scalar multiple, and we've solved the problem. Does that make sense? So we go, okay, well, now the gradient of f is equal to lambda, the LaGrange multiplier, times the gradient of g. So here's the gradient of f. Equal to a scalar multiple, LaGrange multiplier, times the gradient of g. Ladies and gentlemen, do you see where that came from? I don't want to lose you now. You learn too much. Can you do the gradients? Okay, it's easy after that. Said this gradient equal to lambda times the other one. That's all I'm asking you for. You with me? Now let's use some logic here. Can you distribute the lambda?
Yes.
Do you understand that for two vectors to be equal, and these are for sure vectors, that each component has to be equal?
Yeah.
So let's use that. Here's what I know. You with me? Here's what I know. This y has to be equal to 2 lambda. Do you see why? Do you see? I'm going to stick my tongue out forever. Do you see why? Do you see why? I felt like Michael Jordan there for a second doing math.
No.
No? I can't jump that high. Okay, if you do see it, what's x equal to?
3 lambda.
All I heard was rah, rah, rah. But I imagine that you said 3 lambda. Is that what you said?
Yeah.
This class is fun. This class. Seriously though, do you guys see what this is? So set this x component equal to this x component. This y component equal to this y component. Are you with me? And then write down the constraint. Ready? I'm about to tell you your goal in life. Here's your mission in life in this section in this class. It better not be your mission in life. That would suck. Or what? Oh wait, it's basically my life. Doing math all the time. I love it though. It's great. You do math all the time. It's a fantastic job. You should all do. No, wait. I need job security. You all find something else to do. Okay. Okay. So I'm a math teacher. Here's your main goal in life. Solve lambda. Do whatever it takes to solve for lambda, and then plug it in. That's your main goal in life. It can be really, really easy, like this one. Look. I have an equation, correct? Can I substitute something in for x and y that lets me solve for lambda? This is the easiest type, where you have a direct substitution. We go, oh, hey, here's 2 times 3 lambda plus 3 times 2 lambda equals 6. So take y, got it. Take x, got it. Make your substitution, solve for lambda. Your main goal in life right now in this section is solving for that LaGrange multiplier. It's basically like what you do on like direct variation or inverse variation. You have that constant. You got to find the constant first. That's what we're doing. So here we have, oh well, how much? 12 lambda. How much is lambda? Half. Perfect. Now, wait a second. Do you have something up here that would map lambda back to values of x and y?
Yes.
Yeah, these two. We use in concert all three of them. So y equals 2 lambda. X equals 3 lambda. Here's what it tells us. Remember how we found critical points and all that stuff, and then we had to plug in the n values and all that stuff? This right here does everything for you. Because we base it on a contour plot, I know that this right here, how many critical points do you have? 1 critical point. Tell me specifically what it is. 3/2 1. That right there is the 1 critical point we have. That right there is the one point that this constraint is. It's a level curve. That level curve, that constraint is going to bounce off and intersect at one point, one of these level curves. The one where our lambda happens to be 1/2. We plug it in. We find that one specific point. Here's the last piece of information that I need you to know. All constrained maxima and minima will be found at those points. So I know that what these points give us are either maximums or minimums of this function. In this case, did you catch that? You might want to write that one down. No, not constrained. These are absolute with the constraint. So maxima and minima will be found at solutions to this. Maxima and minima will be found as solutions to this. Did you write that down? Write that down. Maxima and minima will be found as solutions to this. To find the actual maxmin, you take this value, just like anything else, plug it in. So what is the value when we plug in this? Well, that's a pretty easy one. 3/2 times 1 is 3/2. Now, what is it? I said maxima and minima happen at that point, but is that a maximum or a minimum? That takes a little bit more work sometimes. If you have 2 points, it's easier because you can tell one's the highest, one's the lowest. You can tell that. If you have only 1 point, here's what's happening. This is either the bottom, a minimum, and everything's climbing higher, or there's a top and everything's climbing lower. This particular one is a max. This is a maximum. How I can tell that, I would have to do the second derivative test. That gives a saddle point, and based on the constraint, what's happening here is for this function, the saddle point gives basically some hyperbolas here, where they're going one way along the x direction below and one way along the y direction above, and where that plane intersects that. Do you see that that's a plane going upward? Where that plane intersects those, it's in one region that everything is climbing higher. That saddle point is climbing higher. You'd need a second derivative test to tell it, but that right there is a maximum value. I'm not going to go into it right now for the sake of time, but that's a max. I want to show you 2 other ones. One other one. What I'm going to do, I'm going to skip over. We have an easy. This was the easy example. We have a really hard one, which I'm gonna hold for next time because it takes a little while to explain it. And then I'm going to show you how to do this with 3 variables. So I'm going to do the 3 variable version first. It's not any harder than this. I just want to show you that you can do it. That's one of the beauties about the LaGrange multiplier, the constraint optimization, is that this stuff, it doesn't matter that you can eliminate a variable. It works with all of this because gradients are easy to find in 3 variables. So I'm going to show you that one, and then we're going to call it good for now, and I'll come back and do one more of these examples next time to really fill it out. Okay, so we're going to try to optimize this function with this constraint. Verify. This is a, wow, it's like a surface in 4D, yeah? It's crazy. This is a constraint. That's 3 variables equal to a constant. This is a level surface of some higher function. So what I want to do right now, here's the process. Keep this function the way it is. Make a function for this such that this is a level surface of some higher function. Let's do that now. Call it G. Can you tell me, please, really quickly, what that function's going to be? Come on, help me. What about the 1? Do I need the 1?
No.
Verify that this is a level surface of that piece of junk.
Yeah.
Okay, cool. Now, the next thing, whether you get it or not, I want you to get it. That's why I spend hours talking about this stuff. Whether you get it or not, the next part's actually pretty easy. Find the gradient for this, find the gradient for this, because that gives us our normals. To level surfaces in the case, and they have to be scalar multiples. So I'm going to give you about 30 seconds. Find me the gradient, it's got to have x, y, z, I, j, k. Find me the gradient, x, y, z, I, j, k. Set them equal by a scalar multiple called lambda or LaGrange multiplier. Let's double check our gradients here. Did you guys get the same gradients that I got? Yeah or no? Yes, yes, no, no. Okay, so if you want to do a shortcut right now and just go x coordinate lambda x component, that's fine. If you really need to build it out and go, well, you know what? I know that the gradient is equal to lambda times the other gradient. That's fine too. So we'd have I plus 2j minus 2k is equal to lambda times 2xi plus 4yj plus 8zk. If you want to build it out like that, that's absolutely fine. The key point here is match up your x components, your y components, and your z components, and get your series of equations. You need to do that. So I want to go really quickly. Come on, I know you're losing focus here. Let me have your focus. Can you tell me what the first equation is going to be, please? Oh, I didn't hear a word you said, honestly.
2x lambda equals 1.
2 what?
X lambda.
Okay, fantastic. Someone else, come on, quickly. What's the next one?
2.
Perfect. And lastly? Beautiful. Yeah, fantastic. Now, the last one I want you to write out the constraint. Whatever the constraint is, that's your last equation. That's an important one. You've got to satisfy that. Hey, how about this? Do you guys see a way to take these 3 equations and use them in this one? Do you guys see a way to do that? How would you do it? Come on, what would you do? Solve for what? If I solve for lambda, I'm not going to have any place to plug it in.
Solve for each variable.
If I solve for x and y like here, I'd have some places to plug it in. Let's try that. Can you double check my work? I get 1 over 2 lambda, 1 over 2 lambda, and 1 over negative 1/4 lambda. Do you guys get the same thing I got? Hey, now that we have these variables and a place to plug them in, do that. Take these variables substitute what they're equal to into that equation. What you're doing here is you're finding the one value of lambda that's going to create a level curve that has, well, lambda that creates the same normal for two different level curves. And where that point exists, that's a max or a min. Then we can simplify it. So if we simplify this, what I got was 1 over 4 lambda squared plus 1 over 2 lambda squared plus another 1 over 4 lambda squared. Head nod if you're okay with that so far. For real. Substitution. Just put it in there. Hey, how would you solve that? Come on, quickly. We got to move kind of quickly on this one.
Common denominator, add together.
Okay, sure. Common denominator, whatever. Multiply everything by the LCD. Doesn't matter. If we multiply everything by 4 lambda squared, then we get 1 plus 2 plus 1 equals 4 lambda squared. Well, that means that if that side adds to 4, lambda squared equals 1. Everybody, please, how much is lambda equal to? What is it?
Plus 1.
Good, we get 2. Hey, do we have something that maps us back from lambdas to x, y, and z values? So the whole idea is, gradients, yeah, set them sort of equal. Lagrange multiplier says they're scalar multiples. That's what that is. Set component for component equal, try any way you can to solve for lambda. Then reverse substitute. So once we find our lambda, we can plug in each 1 and negative 1 to all 3 of these components and figure out what that point is. Do it. Go ahead, try it. So we get the same things that I got. Now, here's what we said before. What we said was, at that point, verify that's one single point. X, Y, Z, one single point for that function. Head nod, yes, no. It also satisfies this thing. That was the whole key here. So we have 1 point, we have 2 points. One of these is going to be the max, one of these is going to be the min. Maxima and minima are found at solutions to this. That was the statement I made earlier. So what we're finding are maxima and minima. Whatever the highest value is, that's our max. Whatever the minimum value is, that's our min. How do you figure out which one's the biggest one and which one's the smallest one? Plug it into where?
The original.
Right there. Plug it in right there. So if we plug it into that, f of this f of that. Plug them in. I've already done it for you. 2 and negative 2. If you can double check me, I think I got those ones right. Hey, that's kind of cool, right? There's no checking. There's no guesswork. What's the maximum value? What's the maximum value of this function based on the fact that we have to satisfy that constraint? What's the maximum value?
2.
Yeah, that's called a constrained maximum. It's the highest that surface gets, but based on the fact that we got to satisfy that. That's kind of cool, right? So this is the max, and this is the min. That's the idea. These are the two values where we have those those scalar multiple normals, where we create that point that we bounce off. One level curve bounces off another one. We happen twice. One of them's the high point, one of them's the low point. Pretty neat, huh? Show of hands if you understand it. Tell you what, we have one more really hard problem. It's hard only because of the substitutions. Obviously, gradients are pretty easy, right? Gradients are pretty easy. This is pretty easy, but doing this, the systems can be kind of tough. So we're going to try that next time. So, as I said, a hard problem. Hard problem. We did one really easy. We did one with 3 variables. Now we got one really hard. The thing that's going to make it hard is the algebra behind it. If you recall, we're working on constrained optimization. Those LaGrange multipliers. And the idea was take level curves, find normals to level curves, it's gradient. They have to be scalar multiples if we're going to share a common normal. That was the plan. So when we're given these two functions, okay, here's your surface, here's your level curve, we must create a surface for that to be a level curve of. That's basically just take your variables. Good. That's the surface, and you can verify it. If I set this equal to 8, I get that specific level curve that is on that surface. Head on that you're with me on that one. After that, we find the gradient of both of these surfaces. This is 2xi plus 2yj. This is 2x plus yi plus what?
2y.
Yeah, we can do it that way. J. Those are the two gradients. Those are the two normals to those level curves of those surfaces. Are you following me? Which means it's a normal to that specific level curve. And we're saying that we want to find the points where these things are scalar multiples. That's why we set them equal to lambda, some constant that we don't know, but we do know at the points we're looking for where the level curves bounce off each other, they will have normals that are scalar multiples. So we force it to happen by finding the lambda, the scalar multiple that makes it happen. Okay, well, that means that 2x plus yi plus 2y plus xj equals lambda. These must be scalar multiples for us to have a common tangent, common normal, that would force those level curves to bounce off each other. That's the main part. That's actually the easy part. I need to show of hands if you see where all this stuff's coming from. Now, the idea is, if I have one vector, verified vector, equal to a scalar multiple of another vector, the components of those vectors, I and j, have to be equal. So I know that 2x plus y must equal lambda times 2x. Does that make sense to you? I also know that 2y plus x has to equal lambda times 2y. Those things have to be there. What I've told you pretty much this whole time is write these down, write down your constraint. The whole goal in life for you in this section is to solve lambda. I've given you 2 ways, and there are 2 different ways to do it. I'm going to give you this third one. It's a third way to do it. I've given you 3 completely different examples to show you 3 different techniques. This one's not going to be that easy. There's a lot of algebra behind it. This was the easy part. Do you understand the idea behind this? That's pretty cool, right? We're setting gradients equal to each other by a scalar multiple. It's called the LaGrange multiplier. That's pretty much it. Our goal is to find that and then substitute back in to solve this thing. So we're going to do that. We're going to go very quickly. It's all algebra. The algebra in calculus, as you know, is the hard part. So I'm going to show you how to do it. I'm going to go fast, though. I'm not going to ask for a lot of comments or feedback. I'm just going to show you the technique here. So the technique. This one, I would solve for y. And I'm going to factor out 2x. So we get y equals 2x lambda minus 1. This one I'm going to solve for x. if we do that, we get this solve for x, subtract the 2y, factor in the same version. You guys understand the algebra on that one. Now, I have to get rid of one of these variables, it doesn't matter which, but I'm going to take this and substitute in for the y here. So x equals 2 times 2x lambda minus 1 times lambda minus 1. Here's the 2, here's the y, here's the lambda minus 1. Can you follow that? Okay, so what we're going to do, since we have one variable now, I'm going to distribute. I'm going to get 0 on one side, and I'm going to use zero product property to figure out some values here. So let's go ahead and let's at least distribute this. So I have 4x lambda minus 1 squared. And if I move everything to one side, we're going to have this 4x lambda minus 1 squared minus x equals 0. And that's the key. That's what I want. If I factor out the x, we're left with that. Listen, I do want to move fast, but I don't want to leave you behind algebraically. Are you guys okay on it's a horrible substitution, but it's kind of a basic substitution. Solving for y, substitute in after you solve for x. You guys get that? That's a system. You can do it. Our goal is to solve lambda. That's what I want. Now, I still have some x's in here, so I'm going to get everything on one side. I'm going to distribute, I'm going to get everything on one side. So 4x lambda minus 1 squared minus x. I'm going to factor the x away. Now, because that's a product, and this is a product of two things equal to 0, I know we have two cases. Either x equals 0 or 4 lambda minus 1 squared minus 1 equals 0. That's got to be the case. One of those two things has to be the case for us to get this equal to 0. Does that make sense? Now, here's the issue. I want to backtrack with this one so you understand that this is irrelevant. Here's why. If I let x equal 0, then 0 and 0 means y would also equal 0. Do you see that? Then x equals 0 and y equals 0. Is that on our constraint? No, because 0 plus 0 does not equal 8. So x equals 0 does not lead anywhere for us. It's an invalid solution because it's not on a constraint. Plug in x equals 0, y is also 0. You go, no. This one is no good. This guy, I told you from the beginning, solve for lambda. You have to solve for lambda. If we do, we have lambda minus 1 squared equals positive 1/4. If we take a square root, we get lambda minus 1 equals plus or minus 1/2. If we take this and separate it, lambda minus 1 equals 1/2, and lambda minus 1 equals negative 1/2. If we add 1, we get lambda equals 3/2, and we get lambda equals 1/2. You guys okay with that? Okay. Now, since we have something that gives us x's, something that relates x's to y's, we're going to take each of these and plug them in for lambda. It's going to give us an equation. So let's use this one. Y equals 2x 3/2 minus 1. That's 1/2. Y equals x. This is where it's going to get fun. What that does, that gives you a substitution to plug into this constraint. So we've done all this work to find a substitution to plug into that constraint. So we go, yeah, find lambda, great, plug it in. What it tells you is not an actual value of x, it tells you a substitution for x or y. It says, yeah, plug it in here. That's exactly what we did. It's right here, this, right there. Plug it in. It's telling you y equals x. Now we take that and we substitute whatever you want. Choose x equals y or y equals x. I don't care. I'm going to choose y equals x. Then x squared plus x squared equals 8. 2x squared equals 8. X equals plus or minus 2. If x equals 2, then y equals 2. If x equals negative 2, then y equals negative 2. Those right there are 2 points that will be either a maxima or minima. That's the plan. How much time do we got? 4 minutes left. Okay, we're going to do another one. If I do the same thing here, we got y equals 2x, and we're going to have 1/2 minus 1. All right, well that means that y equals 2x times negative 1/2. Well, that means that y equals negative x. However, if I take that and plug it in, x squared plus y squared equals 8, when I square a negative, I get a positive. So it's still going to be x squared plus y squared equals 8. It's going to, x squared plus x squared equals 8. It's going to yield the same things. X equals plus 2 or minus 2. However, if you go back to what we used for that, if x equals positive 2, y is the opposite sign. And if x equals negative 2, then y is the opposite sign. That's what that says. So we get some points that look awfully similar. We get the point 2, 2, negative 2, negative 2. 2, negative 2, negative 2, 2. So out of those 4 points, I'm going to write them up here. Out of those 4 points, you tell me this, and then we'll be done. Out of those 4 points, how do you check them? Where do you put them to see which one's the biggest and which one's the smallest? Where do you do? You put them right there to see which is the biggest and smallest. So we're going to evaluate f of all those things. Here's what you can try it on your own. This one is 12. This one's also 12. Nature of the square. This one's 4. This is also 4. Hey, what's the maximum value we attain out of this constrained optimization problem? We learned earlier that these have to create maxima or minima. That's what they do. All maxima and minima will occur at these values with our lambda. What's our max value? Where does it occur? 2 different points. What's our minimum value? Where does it occur? 2 different points. That's our max constrained maxima. That's our min constrained minima. I know the algebra's fast. You might want to go through it a couple times on your own, but that's the idea.